The join function instructs the OS to defer scheduling the calling thread until the other thread finishes. Section 10.2.3. Effect of spawning new threads. In ideal settings, adding a second thread doubles the work we can do in the same amount of time. Each thread can get its work done independently. Reality is not ideal, unfortunately. This has created a myth that threads are slow to create and bulky to maintain. This section aims to dispel that myth. When used as intended, threads perform very well. Listing 10.3 shows a program that measures the overall time taken for two threads to perform the job that was carried out by a single thread in listing 10.2. If adding threads takes a long time, we would expect the duration of listing 10.3's code to be longer. As you'll notice, there's a negligible impact from creating one or two threads. As with listing 10.2, listing 10.3 prints almost the same output. The difference in these two runs on my computer was 0.24 milliseconds. While by no means a robust benchmark suite, it does indicate that spawning a thread isn't a tremendous performance hit. If you've had any experience to the field before, you may have heard that threads don't scale. What does that mean? Every thread requires its own memory, and by implication, will eventually exhaust our system's memory. Before that terminal point, though, thread creation begins to trigger slowdowns in other areas. As the number of threads to schedule increases, the OS scheduler's work increases. When there are many threads to schedule, deciding which thread to schedule next takes more time. Section 10.2.4. Effect of spawning many threads. Spawning threads is not free. It demands memory and CPU time. Switching between threads also invalidates caches. Figure 10.1 shows the data generated by successive runs of listing 10.4. The variance stays quite tight until about 400 threads per batch. After that, there's almost no knowing how long a 20 millisecond sleep will take. And if you're thinking that sleeping is not a representative workload, figure 10.2 shows the next plot, which is even more telling. It asks each thread to enter a spin loop. Figure 10.2 provides features that are worth focusing in on briefly. First, for the first 7 or so batches, the spin loop version returns closer to 20 milliseconds. The operating system's sleep functionality isn't perfectly accurate, however. If you want to sleep pause a thread for short amounts of time, or if your application is sensitive to timing, use a spin loop. Footnote 1. It's also possible to use both, sleep for the bulk of the time and a spin loop towards the end. Second, CPU-intensive multithreading doesn't scale well past the number of physical cores. The benchmarking was performed on a 6-core CPU, the Intel i7-8750H, with hyperthreading disabled. Figure 10.3 shows that as soon as the thread count exceeds the core count, performance degrades quickly. Section 10.2.5. Reproducing the results. Now that we've seen the effects of threading, let's look at the code that generated the input data to the plots in figures 10.1 through 10.2. You are welcome to reproduce the results. To do so, write the output of listings 10.4 and 10.5 to two files, and then analyze the resulting data. Listing 10.4, whose source code is available at c10/ch10-multijoin/src/main.rs, suspends threads for 20 milliseconds with a sleep. A sleep is a request to the OS that the thread should be suspended until the time has passed. Listing 10.5, whose source code is available at c10/ch10-busythreads/src/main.rs, uses the busy wait strategy, also known as busy loop and spin loop, to pause for 20 milliseconds. The control flow we've chosen for lines 9 through 21 is slightly odd. Rather than iterating through the handles vector, we call pop and then drain it. The following two snippets compare the more familiar for loop, listing 10.6, with the control flow mechanism that is actually employed, listing 10.7. Why use the more complex control flow mechanism? It might help to remember that once we join a thread back to the main thread, it ceases to exist. Rust won't allow us to retain a reference to something that doesn't exist. Therefore, to call join on a thread handler within handlers, the thread handler must be removed from handlers. That poses a problem. A for loop does not permit modification to the data being iterated over. Instead, the while loop allows us to repeatedly gain mutable access when calling handlers.pop. Listing 10.8 provides a broken implementation of the spin loop strategy. It is broken because it uses the more familiar for loop control flow that was avoided in listing 10.5. You'll find the source for this listing in this file. Its output follows the listing. Here is the output generated when attempting to compile listing 10.8. This error is saying that taking a reference isn't valid here. That's because multiple threads might also be taking their own references to the underlying threads, and those references need to be valid. Astute readers know that there is actually a simpler way to get around this problem than what was used in listing 10.5. As the following listing shows, simply remove the ampersand. What we've encountered is one of those rare cases where taking a reference to an object causes more issues than using the object directly. Iterating over handlers directly retains ownership. That pushes any concern about shared access to the side, and we can proceed as intended. Yielding control with thread yield_now. As a reminder, the busy loop within listing 10.5 includes some unfamiliar code, repeated in the following listing. This section explains its significance. std thread yield_now is a signal to the OS that the current thread should be unscheduled. This allows other threads to proceed while the current thread is still waiting for the 20 milliseconds to arrive. The downside to yielding is that we don't know if we'll be able to resume at exactly 20 milliseconds. An alternative to yielding is to use the function std sync atomic spin_loop_hint. Spin_loop_hint avoids the OS. Instead, it directly signals the CPU. A CPU might use that hint to turn off functionality, thus saving power usage. Note: the spin_loop_hint instruction is not present for every CPU. On platforms that don't support it, spin_loop_hint does nothing. Section 10.2.6 Shared Variables. In our threading benchmarks, we created pause variables in each thread. If you're not sure what I'm referring to, the following listing provides an excerpt from listing 10.5. We want to be able to write something like the following listing. The source for this listing is in this file. If we run listing 10.12, we'll receive a verbose and surprisingly helpful error message. The fix is to add the move keyword to where the closures are created, as hinted in section 10.2.1. The following listing adds the move keyword, which switches closures to use move semantics. That, in turn, relies on copy. The details of why this works are interesting. Be sure to read the following section to learn those. Section 10.3 Differences between closures and functions. There are some differences between closures, or two vertical bars followed by curly braces, and functions, FN. The differences prevent closures and functions from being used interchangeably, which can cause problems for learners. Closures and functions have different internal representations. Closures are anonymous structs that implement the std ops fn once trait and potentially std ops fn and std ops fn mute. Those structs are invisible in source code but contain variables from the closure's environment that are used inside it. Functions are implemented as function pointers. A function pointer is a pointer that points to code, not data. Code, when used in this sense, is computer memory that has been marked as executable. To complicate matters, closures do not enclose any variables from their environment are also function pointers, forcing the compiler to reveal the type of closure. The concrete type of a Rust closure is inaccessible as source code. The compiler creates it. To retrieve it, force a compiler error like this. Among other errors, the compiler produces this when attempting to compile the snippet as /tmp/a-plus-b.rs. Section 10.4. Procedurally generated avatars from a multi-threaded parser and code generator. This section applies the syntax that we learned in Section 10.2 to an application. Let's say that we want the users of our app to have unique pictorial avatars by default. One approach for doing this is to take their usernames and the digest of a hash function, and then use those digits as parameter inputs to some procedural generation logic. Using this approach, everyone will have visually similar yet completely distinctive default avatars. Our application creates parallax lines. It does this by using the characters within the base 16 alphabet as opcodes for a logo-like language. Section 10.4.1. How to run render hex and its intended output. In this section, we'll produce 3 variations. These will all be invoked in the same way. The following listing demonstrates this. It also shows the output from invoking our render hex project, listing 10.18. Any stream of valid base 16 bytes generates a unique image. The file generated from echo Rust in action in single quotes piped to SHA-256 sum renders as shown in Figure 10.4. To render SVG files, open the file in a web browser or a vector image program such as Inkscape, found at inkscape.org. Section 10.4.2. Single-threaded render hex overview. The render hex project converts its input to an SVG file. The SVG file format succinctly describes drawings using mathematical operations. You can view the SVG file in any web browser and many graphics packages. Very little of the program relates to multithreading at this stage, so I'll skip much of the details. The program has a simple pipeline comprised of 4 steps. 1. Receives input from stdin. 2. Parses the input into operations that describe the movement of a pen across a sheet of paper. 3. Converts the movement operations into its SVG equivalent. 4. Generates an SVG file. Why can't we directly create path data from input? Splitting this process into 2 steps allows for more transformations. This pipeline is managed directly within main. The following listing shows the main function for render-hex, listing 10.18. It parses the command line arguments and manages the SVG generation pipeline. You'll find the source for this listing in this file. Input parsing. Our job in this section is to convert hexadecimal digits to instructions for a virtual pen that travels across the canvas. The operation enum shown in the following code snippet represents these instructions. Note: the term operation is used rather than instruction to avoid colliding with terminology used within the SVG specification for path drawing. To parse this code, we need to treat every byte as an independent instruction. Numerals are converted to distances, and letters change the orientation of the drawing. Interpret instructions. The artist struct maintains the state of the diagram. Conceptually, the artist is holding a pen at the coordinates x and y and is moving it in the direction of heading. To move, artist implements several methods of the render-hex project, two of which are highlighted in the following listing. Rust's match expressions are used to succinctly refer to and modify internal state. You'll find the source for this listing in this file. The convert function in listing 10.16 is an extract from the render-hex project, listing 10.18. Makes use of the artist's struct. Its role is to convert the vec of operation from parse to a vec of command. That output is used later to generate an SVG. As a nod to the logo language, artist is given the local variable name turtle. The source for this listing is in this file. Generating an SVG. The process of generating the SVG file is rather mechanical. Generate_SVG, lines 161 through 192 of listing 10.18, does the work. SVG documents look a lot like HTML documents, although the tags and attributes are different. The path tag is the most important one for our purposes. It has a D attribute, D is short for data, that describes how the path should be drawn. Convert produces a vec of command that maps directly to the path data. Source code for the single-threaded version of render-hex. The render-hex project has an orthodox structure. The whole project sits within a fairly large main.rs file managed by Cargo. To download the project source code from its public code repository, use the following commands. Otherwise, to create the project by hand, follow the commands in the following snippet, and then copy the code from listing 10.18 into src/main.rs. The standard project structure, which you can compare against the following snippet, has been created for you. The following listing shows the metadata for our project. You should check that your project's cargo.toml matches the relevant details. You'll find the source for this listing in this file. The single-threaded version of render-hex appears in the following listing. You'll find the source for this listing in this file. Section 10.4.3. Spawning a thread per logical task. Our render-hex project, listing 10.18, also presents several opportunities for parallelism. We'll focus on one of these, the parse function. To begin, adding parallelism is a two-step process. 1. Refactor code to use a functional style. 2. Use the rayon crate and its par_iter method. Using a functional programming style. The first step in adding parallelism is to replace our for. Rather than for, the toolkit for creating a vec of t with functional programming constructs includes the map and collect methods and higher order functions, typically created with closures. To complete the two styles, consider the differences to the parse function from listing 10.18 in ch10-render-hex/src/main.rs, repeated in the following listing, and a more functional style in listing 10.20 in this file. Listing 10.20 is shorter, more declarative, and closer to idiomatic Rust. At a surface level, the primary change is that there is no longer a need to create a temporary variable steps. The partnership of map and collect removes the need for that. Map applies a function to every element of an iterator, and collect stores the output of an iterator into a vec of t. There's also a more fundamental change than eliminating temporary variables in this refactor, though. It has provided more opportunities for the Rust compiler to optimize your code's execution. In Rust, iterators are an efficient abstraction. Working with their methods directly allows the Rust compiler to create optimal code that takes up minimal memory. As an example, the map method takes a closure and applies it to every element of the iterator. Rust's trick is that map also returns an iterator. This allows many transformations to be chained together. Significantly, although map may appear in multiple places in your source code, Rust often optimizes those function calls away in the compiled binary. When every step that the program should take is specified, such as when your code uses for loops, you restrict the number of places where the compiler can make decisions. Iterators provide an opportunity for you to delegate more work to the compiler. This ability to delegate is what will shortly unlock parallelism. Using a parallel iterator. We're going to cheat here and make use of a crate from the Rust community, Rayon. Rayon is explicitly designed to add data parallelism to your code. Data parallelism applies the same function, or closure, on different data, such as a vec of t. Assuming that you've already worked with the base render-hex project, add Rayon to your crate's dependency with cargo by executing cargo add rayon at 1. Ensure that the dependencies surrounded in a square brackets section of your project's cargo.toml matches the following listing. You'll find the source for this listing in this file. At the head of the main.rs file, add Rayon and its prelude as listing 10.23 shows. Prelude brings several traits into the crate's scope. This has the effect of providing a par_bytes method on string slices and a par_iter method on byte slices. Those methods enable multiple threads to cooperatively process data. The source for this listing is in this file. Using Rayon's par_iter here is a cheat mode available to all Rust programmers, thanks to Rust's powerful std iter iterator trait. Rayon's par_iter is guaranteed to never introduce race conditions. But what should you do if you do not have an iterator? Section 10.4.4. Using a thread pool and task queue. Sometimes we don't have a tidy iterator that we want to apply a function to. Another pattern to consider is the task queue. This allows tasks to originate anywhere and for the task processing code to be separated from task creation code. A fleet of worker threads can then pick tasks once these have finished their current one. There are many approaches to modeling a task queue. We could create a vec of task and vec of result and share references to these across threads. To prevent each thread from overwriting each other, we would need a data protection strategy. The most common tool to protect data shared between threads is arc of mutex of t. Fully expanded, that's your value t, e.g. vec of task or vec of result here, protected by a std sync mutex, which itself is wrapped within std sync arc. A mutex is a mutually exclusive lock. Mutually exclusive in this context means that no one has special rights. A lock held by any thread prevents all others. Awkwardly, a mutex must itself be protected between threads. So we call in extra support. The arc provides safe multi-threaded access to the mutex. Mutex and arc are not unified into a single type to provide programmers with added flexibility. Consider a struct with several fields. You may only need a mutex on a single field, but you could put the arc around the whole struct. This approach provides faster read access to fields that are not protected by the mutex. A single mutex retains maximum protection for the field that has read-write access. The lock approach, while workable, is cumbersome. Channels offer a simpler alternative. Channels have two ends, sending and receiving. Programmers don't get access to what's happening inside the channel, but placing data at the sending end means it'll appear at the receiving end at some future stage. Channels can be used as a task queue because multiple items can be sent even if a receiver is not ready to receive any messages. Channels are fairly abstract. These hide their internal structure, preferring to delegate access to two helper objects. One can send, the other can rec-v or receive. Importantly, we don't get access to how channels transmit any information sent through the channel. Note: by convention from radio and telegraph operators, the sender is called TX, shorthand for transmission, and the receiver is called RX. One-way communication. This section uses the channels implementation from the Crossbeam crate rather than from STD Sync MPSC module within the Rust standard library. Both APIs provide the same API, but Crossbeam provides greater functionality and flexibility. We'll spend a little time explaining how to use channels. If you would prefer to see them used as a task queue, feel free to skip ahead. The standard library provides a channels implementation, but will make use of the third-party crate Crossbeam. It provides slightly more features. For example, it includes both bounded queues and unbounded queues. A bounded queue applies back pressure under contention, preventing the consumer from being overloaded. Bounded queues of fixed width types have deterministic maximum memory usage. These do have one negative characteristic, though. They force queue producers to wait until a space is available. This can make unbounded queues unsuitable for asynchronous messages, which cannot tolerate waiting. The Channels-Intro project, listings 10.23 and 10.24, provide a quick example. Here is a console session that demonstrates running the Channels-Intro project from its public source repository and providing its expected output. To create the project by hand, follow these instructions. 1. Enter these commands from the command line. 2. Check that the project's cargo.toml file matches listing 10.23. 3. Replace the contents of src/main.rs with listing 10.24. The following two listings make up the project. Listing 10.23 shows its cargo.toml file. Listing 10.24 demonstrates calling a channel for I32 messages from a worker thread. Some notes about the Channels-Intro project. Creating a channel with Crossbeam involves calling a function that returns sender of T and receiver of T. Within listing 10.24, the compiler infers the type parameter. TX is given the type sender of I32, and RX is given the type receiver of I32. The select exclamation point macro takes its name from other messaging systems like the POSIX sockets API. It allows the main thread to block and wait for a message. Macros can define their own syntax rules. That is why select exclamation point macro uses syntax rec of RX with a single right arrow. That is not legal Rust. What can be sent through a channel? Mentally, you might be thinking of a channel like you would envision a network protocol. Over the wire, however, you only have the type U8 surrounded in square brackets available to you. That byte stream needs to be parsed and validated before its contents can be interpreted. Channels are richer than simply streaming bytes, U8 surrounded in square brackets. A byte stream is opaque and requires parsing to have structure extracted out of it. Channels offer you the full power of Rust type system. I recommend using an enum for messages as it offers exhaustive testing for robustness and has a compact internal representation. Two-way communication. Bidirectional or duplex communication is awkward to model with a single channel. An approach that's simpler to work with is to create two sets of senders and receivers, one for each direction. The Channels-Complex project provides an example of this two-channel strategy. Channels-Complex is implemented in listings 10.25 and 10.26. These are available in this file and this file, respectively. When executed, Channels-Complex produces 3 lines of output. Here is a session that demonstrates running the project from its public source code repository. Some learners prefer to type everything out by hand. Here are the instructions to follow if you are one of those people. 1. Enter these commands from the command line. 2. Check that the project's cargo.toml file matches listing 10.25. 3. Replace src/main.rs with the contents of listing 10.26. Implementing a task queue. After spending some time discussing channels, it's time to apply these to the problem first introduced in listing 10.18. You'll notice that the code that follows shortly in listing 10.28 is quite a bit more complex than the parallel iterator approach seen in listing 10.24. The following listing displays the metadata for the channel-based task queue implementation of render-hex. The source for this listing is in this file. The following listing focuses on the parse function. The rest of the code is same as listing 10.18. You'll find the code for the following listing in this file. When independent threads are introduced, the order in which tasks are completed becomes non-deterministic. Listing 10.28 includes some additional complexity to handle this. Previously, we created an empty vec of command for the commands that we interpret from our input. Once parsed, main repeatedly adds elements via the vector's push method. Now, at line 147, we fully initialize the vector. Its contents don't matter. It will all be overridden. Even so, I've chosen to use command no-op to ensure that a mistake won't result in a corrupt SVG file. Section 10.5, Concurrency and Task Virtualization. This section explains the difference between models of concurrency. Figure 10.5 displays some of the trade-offs. The primary benefit of more costly forms of task virtualization is isolation. What is meant by the term isolation? Isolated tasks cannot interfere with each other. Interference comes in many forms. Examples include corrupting memory, saturating the network, and congestion when saving to disk. If a thread is blocked while waiting for the console to print output to the screen, none of the coroutines acting in that thread are able to progress. Isolated tasks cannot access each other's data without permission. Independent threads in the same process share a memory space, and all threads have equal access to data within that space. Processes, however, are prohibited from inspecting each other's memory. Isolated tasks cannot cause another task to crash. A failure in one task should not cascade into other systems. If a process induces a kernel panic, all processes are shut down. By conducting work in virtual machines, tasks can proceed even when other tasks are unstable. Isolation is a continuum. Complete isolation is impractical. It implies that input and output is impossible. Moreover, isolation is often implemented in software. Running extra software implies taking on extra runtime overhead. A small glossary of terms relating to concurrency. This subfield is filled with jargon. Here is a brief introduction to some important terms and how we use them. Program. A program, or application, is a brand name. It is a name we use to refer to a software package. When we execute a program, the OS creates a process. Executable. A file that can be loaded into memory and then run. Running an executable means creating a process and a thread for it, then changing the CPU's instruction pointer to the first instruction of the executable. Task. This chapter uses the term task in an abstract sense. Its meaning shifts as the level of abstraction changes. When discussing processes, a task is one of the process's threads. B. When referring to a thread, a task might be a function call. C. When referring to an OS, a task might be a running program, which might be comprised of multiple processes. Process. Running programs execute as processes. A process has its own virtual address space, at least one thread, and lots of bookkeeping managed by the OS. File descriptors, environment variables, and scheduling priorities are managed per process. A process has a virtual address space, executable code, open handles to system objects, a security context, a unique process identifier, environment variables, a priority class, minimum and maximum working set sizes, and at least one thread of execution. Each process is started with a single thread, often called the primary thread, but can create additional threads from any of its threads. Running programs begin their life as a single process, but it isn't uncommon to spawn sub-processes to do the work. Thread. The thread metaphor is used to hint that multiple threads can work together as a whole. Thread of execution. A sequence of CPU instructions that appear in serial. Multiple threads can run concurrently, but instructions within the sequence are intended to be executed one after another. Coroutine. Also known as fiber, green thread, and lightweight thread, a coroutine indicates tasks that switch within a thread. Switching between tasks becomes the responsibility of the program itself, rather than the OS. Two theoretical concepts are important to distinguish.